Hi, everyone. So excited to be here today to talk to you about the Multimodal Lakehouse, a new foundation for AI data. My name is Chang She. I'm the CEO and co-founder of LanceDB. I've been building data tools for machine learning and AI for almost 2 decades. I was one of the original co-authors of the Pandas library, and I've spent years building recommender systems, personalization, and machine learning infrastructure at 2BTV, a streaming company. And it was through that experience that motivated me to start working on LanceDB to better enable teams building AI applications and models. Because what I noticed was that there is a whole set of new kinds of data and workloads that don't fit neatly into those pandas data frames that needs a better data infrastructure and a better data foundation. AI has, of course, taken the world by storm the last few years. We all know that. Models and applications have advanced far since the first release of ChatGPT. But now everyone has access to the same models. And the best techniques for building agents or prompt engineering are diffusing throughout the industry. So, in this world where everyone has access to the same models, the same techniques, you got to ask yourself, what's going to differentiate your AI features? Are we just wasting time building AI when it's all going to look the same? Well, the answer is data. Specifically, how you're able to connect your data to your AI makes the difference between a commodity versus a highly differentiated product. Now, we've heard this refrain before. If you worked in the classical ML era, there are for sure lots of parallels that can be drawn between then and now. But with AI, there are many unique characteristics about this new set of data and this new generation of technology that's fundamental to new data challenges. And so it's interesting to see and draw parallels in history. But this time around, it's really the differences that's interesting that matter. Okay, let's take a trip down memory lane. Back in 2001, there was a Gartner study that published what was called the three V's of big data. And it stuck around as the most useful framework when looking at data infrastructure. Specifically, the three V's are volume, which is the amount of data that's being stored or managed, velocity, or the speed at which this data is being generated, and then variety, the kinds of data that you're dealing with. And so, actually, this is a super useful framework still. And using this familiar framework, let's look at how AI data is different today. First, there's volume. In the past, tabular data rows typically tends to be fairly small. If you look at the typical TPCH table, it's around 150 bytes per row. Once you add embeddings and then images and audio and video signals into that table, into that mix, it becomes much bigger. In fact, it can get up as far as 6 orders of magnitude bigger. So the volume of data today, even if it's the same number of observations, is just a lot bigger than before. Not only that, but this data is being generated a lot faster now. Earlier this year, a study published by Amazon concluded that 57% of all web based text has been AI generated or translated through an AI algorithm. And of course, there are various arguments and debate about whether this is true or not, or whether this is an overestimate. But increasingly, what's not up for debate is the fact that we are no longer limited by the speed at which humans are manually generating data. Instead, images and text, you think emails or images and videos are being generated at hundreds of tokens per second by the model. Number three, it's not just about tabular data anymore. It's not just about time series or numbers. It's now about long form text. It's now about generated images and videos. It's about real time translation of audio signals. And to make all of that data searchable, it's more than just SQL, but it's about embedding search and it's about indexing. So the variety of data and the variety of indexes and the variety of workloads have gone up as well. When we put those three phenomena together, It means that traditional data lakes are no longer a good fit at all for AI. It forces you to manage multiple systems for different types of data and workloads and creates a lot of unnecessary complexity, not to mention prohibitively high cost. So, one quick example here is, let's say you try to scale up on search. You have to copy part of your data from the data lake into a system like, say, Elasticsearch. That copy can often be complicated, error prone, and expensive. Moreover, systems like Elasticsearch, made for a previous generation of search, doesn't really support compute storage separation. So when you scale up on vector volume, for example, it's extremely costly and it's very complicated to manage sharding and rebalancing and joining and removing of nodes for auto scaling. Another example is for training. If you're using TF records or web dataset to store your training data, it's almost impossible to add more model features without copying the entire data set. Now, for multimodal data sets, it's pretty often that we see um, image and video data sets for training that goes up to petabytes or tens of petabytes. So that simple copy operation and computing a new feature can often take many extra hours or even days. And the impact is not just about the cost or slow running processes. Having to manage many different systems can drastically reduce research productivity. Again, history rhymes here, as you can see from this decade old tweet about how data scientists expected to spend their time versus how they actually spend their time. And even though AI is increasingly replacing human labor, human time is still worth a lot more than CPU or GPU time. Well, perhaps you could say because AI gives us a lot more leverage, human time is worth even more now than before. So, can we do better? Is there a world where storing and working with AI data is just much easier, less costly, and can we have infrastructure that improves rather than hinders our productivity? Well, given the fact that I'm giving this talk, you can probably guess that my answer is yes. So the challenges that we've talked about with AI data starts right from the foundations, from the storage layer. So the right solution also needs to rebuild that foundation. So rather than another vector database, what we need really is a new lakehouse architecture. Because of the limitations of, let's say, row groups and Parquet, legacy formats like these and anything that's based on Parquet is not a great fit for storing AI data. It's also not a good fit for training and search workloads because they require fast random access, meaning I need to be able to fetch 10 rows spread out throughout the data set of, let's say, a billion rows or something like that. Instead, we need a new format that actually supports storing all that together, forming a new foundation, and that can deliver blazing fast performance across a diverse set of queries, and also avoids the need for siloed storage. And this format, of course, needs to be open source because we have such a diverse set of workloads that we need to run that you need to be able to access this data from a rich ecosystem of tools like Spark and PyTorch and Ray and many new data frame and compute engines. Okay, so first, let's talk about this new foundational format, what we call Lance format. So Lance targets AI workloads natively instead of as an afterthought after optimizing for, say, let's say TPCH or analytical workloads. And this format solves the following problems, right? So one, how can we store multimodal data and tabular data all in the same table? Two, how can we enable both big data and AI workloads efficiently at scale? And how do we support the ability to do fast scans for analytics? This is done via the columnar nature of the format. How do we support constant time random access for search, right? So the Lance format delivers a different layout, it has different encodings, and it uses secondary indices to speed that up even more. And number three, how do we manage large blob data efficiently? Is when you have a mix of small, narrow columns and large and wide columns, how do we deal with that? Well, we do that by getting rid of row groups, and we have an innovative two-dimensional layout. Typically, the existing systems and the systems, other systems that are under development today, can handle one or at most two of these. But to be successful for AI, especially multimodal AI, we need all three. And so we call this the new CAP theorem for AI data, of course, jokingly. And some of this capability belongs at the file format level. Others traditionally at what's called the table format level. Lance also adds secondary indices, so full text search, vector search, um, scalar search for filters like B trees and bitmaps and things like that, which isn't in either level of format. And because they all work in tandem with each other, uh, we feel that the future is having these things together as a single format rather than having separate things, each doing their own job and trying to integrate amongst these. So we're calling Lance a lakehouse format, or more appropriately, a multimodal lakehouse format. The advantage of having this format is to support unified storage and a diverse set of access patterns. We support multiple workloads across all of your AI workflows so that you can have a single table that stores not just numbers and strings, but also long form text, vectors, and sometimes multiple vectors, right? So we can support analytics to search queries to data pre-processing, feature engineering. It allows you to incrementally add to your table and enrich your features with additional features. So these embedding columns, for example, can be generated from the text columns, right? And tabular data columns can be used as filter columns to limit embedding search. So all of these things can work together, and for a lot of production AI applications, has to work together to deliver the best quality AI models or AI retrieval. Let's talk a little bit about data evolution and the table in a changing world. So, for example, before you can have a clean data set that's searchable or that's fit for plugging into PyTorch into a GPU for training, you need to extract features, say chunks, and then compute embeddings from those chunks. And moreover, data enrichment process is often incremental, right? Later stage features depends on earlier feature pipeline stages. So it's extremely important that researchers are able to do things like add features without copying the original table, incrementally add both columns and rows, and be able to track the evolution of this data over time. So to solve this problem, LAN supports what we call zero copy data evolution. It's more than just seam evolution where you're just adding additional columns, but it's about adding columns and rows and then backfill and being very careful about not having to copy a table of images or videos that might be petabytes large. So when you put all of this together, right, this is where we move from the problem to what a solution looks like. You have one place to put all of your AI data in object storage for cost efficiency. And this storage layer is completely open source. You can plug that into the data tooling that you want and are familiar with, whether it's PyTorch or Spark or Ray. And you can run multiple workloads for training, for pre-processing, for analytics, and search on top of this data, on top of this lakehouse with compute storage separation. And finally, the ability to incrementally enrich your data makes it a lot easier for you to add additional features and add value to your data sets over time without having to repeat a lot of storage and do redundant calculations. Okay, so for the community, for the users that are using Lance and LanceDB, there's a lot of benefits, but one amongst them is to get massively scalable search on object store, which is extremely performant and cost efficient. Right. The fact that we store the data on object store and the fact that the search indices and secondary indices are disk based rather than RAM completely changes the cost curve as you scale up on AI. So if you look at AWS pricing, for example, going from RAM to S3 means the difference between 2 cents per hour to 2 cents per month for 1 GB. Beyond the cost, it's just a lot easier and a lot simpler as the core foundation of your AI stack, because now not only can you run search, you don't actually have to move data to run that search, and you don't have to move your data to do transformations on that data or to train a model on that data. And all that combined delivers a lot a lot lower feature engineering time. It saves human time from new features taking weeks to to a set of hours. So beyond the storage layer and the computational workloads that I mentioned, if we look across the infrastructure landscape, it's actually clear that a rich new ecosystem is forming around the set of new AI data challenges. Right? And there's three new trends that I found to be very interesting. So in 1916, an evolutionary biologist named Lancelot, which is actually really funny given our project name is Lance. I would call that convergent evolution. He coined the term called carcinization because he noticed that many non-crab crustacean species actually independently evolve crab-like body plans. Well, so this is the phenomenon this is the term that's being used to call the phenomena where a lot of the new data projects are eschewing languages like JVM and C++ for Rust, and many, mostly independently, and many for different reasons. But a lot of that is for the fact that Rust gives you um, the productivity of JVM and the safety of JVM, but the performance of a C++ like ecosystem. Number two is that multimodal data is becoming a first class citizen. Instead of optimizing for TPCH and analytical workloads, we're now focusing on search and training and handling of multimodal data, where PDFs, audios, and video is becoming a first class citizen in the design and the core of new data systems. And thirdly, we're moving from purely focused on developer experience to AI or agent experience, where documentation, promptability, and focus on having clear examples and integrations like MCP servers is now an important part of designing new libraries and new tools. So for a new foundation like Lance, it is already an important part of the ecosystem, the community that's powering the future of AI development. Over the past year, Lance open source was downloaded more than 20 million times, and it's being used across a large number of frontier model companies, leading agent companies, and then large data infrastructure companies that build on top of Lance and LanceDB. So to look a little bit into the future for what it looks like for this new standard for AI data, the work that we have ongoing in this quarter and the rest of the year is around connecting it to even more parts of the data ecosystem. So moving from Spark and Ray to things like data catalogs, Flink, and Trino, and then adding additional compression and encodings, and then finer grained features for the data format that improves performance, allows us to deal with even larger blobs, and the ability to go from billions of vectors to maybe trillions of vectors. So got a lot of exciting things to deliver over the rest of the year. And of course, we already have a lot of external contributors, but we would love for like-minded folks to come join us and work on this with us together. So thank you so much for attending my talk. You can download our white paper about the multimodal lakehouse in this QR code that I've thrown up here. And I'd love to hear from you, whether you have questions or you want to work on Lance and LanceDB together with us. Thank you.